Hello everyone, my name is Weiqi Wang. I'm currently working at University of Manchester with Marie Farrell, Lucas Cordero, and Liping Zhao. I'm so excited to share our work with you on supporting software formal verification with large language models. Essentially, it's about we use large language model to bridge the gap between natural language and the formal verification properties. Let me begin with something we all know. Formal verification could be very complex for many people because many domain experts lack the knowledge to use the tools. So the current reality is requirement engineers, we write the requirement in natural language, right? But we still need to work with some verification expert so we can translate the requirement to the formal properties and the system can verify it. However, this process creates some key barriers. First, we need and the expert need to understand the tools, like multiple tools for formal verification. And the second one is we still need some manual step to mapping the variables between the requirement and the implementation variables. Besides that, many tools like Housing and the rest, they have some limited expressiveness for complex temporal dependency, like for some constraint they cannot explain in the system automatically. So they still need some manual steps. And what we want to do is we can enable directly automation from formal verification for the domain experts. So let me show our approach. Let me show you our approach. And you are here. You are provided with some system requirement and specification. You might also provide with us some system implementation in C, or maybe you can translate them to C. I later am to it's two main step over here. The phase one over here we call the formalization requirement and the test design. We give ARM with a structured guidance for information selection. Think of this as a roadmap so the ARM can understand what is more important in your document and it can translate to a format what you want to verify, right? And after that, because the ESBMC works in the C code or C++, and we here use C, and we give the second phase here to generate the structured guidance for ESBMC assertion and the basic rule. So it provides the property in the C format. After that, finally, ESBMC can get the implementation and the property and give you results. We also do the validation over the code. We can compare on the verification rates, the logic equivalence, and did we give any like false positive or false negative. And here is I want to say why we think LLM can do quite well on our task. Here is some example during our experiment. And here is a question if large language model could bridge the gap between natural language and formal property on semantic. The input is over here, output should be bounded by the top and the bottom limit. It actually, large language model didn't directly translate it to a simple property. It actually need multiple conditions so we can conduct the formal verification. First, we need to check the upper boundary checking. We put this in assertion, so when it's valid, it will be report. And for the lower bound, look like that. Edge case handling in the system, this is the edge case that when this happens, it should be another value. And the LLM understand that. Error state transition, it's like when you input some invalid setup, like the top, they send the button, and okay, now the top is the button. All right. And the insight over here is we got a single requirement sentence, and the LLM, based on its understanding, generate multiple formal properties automatically. The example here, the second one is for mathematical reasoning, we called it. The input look like that. Maintain target on port side of vehicle. He- This case reveals more complex understanding for of LLM. First, LLM need to understand what I mean by port side. It means left side in navigation. And after that, it found, okay, spectacle relationship should be changed to geometric constraints. And it formalize a mathematical constraint. It provide a cross product and do the test. So here is a formal specification. We got a precondition. We need to check if the position both of vehicle and target is valid before do the test. Okay. And after that, we got some post condition. Post condition is cross product z should be less than 0. But what is cross product z? It means by target x minus vehicle s and multiple vehicle velocity y and should be less than zero, right? So we got the key insight over here is the domain knowledge is not a large challenge for LLM. It can change the port size to a mathematical constraint automatically. However, we also face some challenges during our experiment. We've got the challenge we call domain-specific semantic interpretation. This is from TSM system. There is a word called miscompare. And the requirement document recognizes that error would appear as a difference called a miscompare. LLM think, okay, miscompare means difference between signal. That makes sense. But in reality, it's not. It's actually a triple redundancy voting system, so the majority wins. I think the root issue here is the word could be a terminology words, so you have different words and the common words, but error could be misled by the document or some general source. This is a implicitation for requirement engineering that when you use automation tools, you should provide a explicit domain context, and the requirements should be defined their key terminology. 3.4% of our case have this problem. That's like for two, right? And the challenge two is like more important one. This is we call boundary problem in AI requirements. It's from a swim system. It's a short one, and it's actually a airspeed monitoring system. The requirement look like that. It monitors the press should be not less than the trigger. And the ESBMC got a violation and say, okay, we got to navigate press values that make no sense, and that's a counterexample. However, we found Coxing didn't report that, and we tracing back and see what happened. And we found Coxing, the group, they manually add a assumption. It's called aircraft growth weight less than 0. That makes sense, very obvious to human. However, we consider that's a biggest dilemma for large language model because this human decision could be designed by like a domain knowledge or some experts they have consulted with. But how could we let AI do the decision alone? So that's not a that's a big issue for large language model. And the current state is LLM cannot replicate expert constellation process alone, right? We need some communication with it. And here I want to show how we check we are verifying the same property with like the human expert doing. We compare with the Cocosing team and we use ON logic. ON logic is defined like we got some precondition, we got some process to do, and after that we got some result like post condition. Here is an example we localize that. It's in raster, so it's an abstract description of the system. And after that, and we are the same, but we are already mapping to the C code. And for the manually analyze, you need to compare the condition like post, pre, right? And after that, we also need to map, okay, if the abstraction is same with what we use in our C implementation. We also need to verify if the logic, like the function or something, they are all the same. However, it's quite time consuming because no automatically tool existing inside because it's different language. And the result is 79.31% logic is equivalent across 58 requirement sentence. Now let me show our benchmark result. We compare with Cocosync, it's NASA group, and the SLDV is from Simulink model. And you can see over here we got 46.5% verification rate, which matches the Cocosync result, and we are 28% better than SLDV. We got zero false positive compared with focusing to false positive. We got fewer false negative, and we want to say our key advantage. We got fully automation, no manual mapping needed, and we can express better than LTL. Look, you can look over here. Look at we can express more and verify more properties. We found two new floating point error that SLDV refused to answer and Cocosync cannot. The remaining challenge is we can still not verify narrow network and complex metrics. Our technical discovery for the floating point precision error. Here is one example from the TSM system for the median selection algorithm. We got three inputs, and you can see A is extremely large, B is nearly zero, and C 1.9. So we should select C. However, their implementation have some bugs, so they use mean-based selection instead of a directly comparison. And then because of IEEE 756 processing rules, when you're doing that, use a mean instead of directly comparison, some rounding error would happen, and as a result, is select B as the closest. And both verification approach test the same property based on comparison based. And we found the result is different. Cocosync missed this bug because it uses Russian number. SLDV and ESBMC found it because we are implementing IEEE 756 for input accuracy. We also confirm it by running the code. We generate the test case based on the example as the input, and we can check the output. And also, SLDV refused to answer in some floating point issues, so we found more. The key insight over here is implementation error, verification review error hidden by mathematical abstraction. Another thing we want to share with you is manual verification step and abstraction could introduce some error. The case one over here is the Simulink whiling error for Cocosync because their team they need manually mapping, right? They got some block and they need to map to another block. This is for a counter and they falsely connect to zero. So you introduce some error because of manual connection. And the case two is for the lookup table because calculate cosine and sine is actually quite expensive as they try to use some lookup table to simplify it. And however, you can see over here, the cosine for 3 over 2 pi should be 0, but they give like 1 over 2 or minus 1 over 2. And all the six error is caused because of the approximation inconsistency. So we got two lesson manual step called introduce some error. And when human want to manually abstraction some code, it could also introduce some error. Here is some summary for our research. We got end-to-end automation from requirement to C code. We found floating point precision error missed by Cocosync. We reduce manual modeling error, like wiring approximation. And we also have some insights for requirement engineering. We think, okay, domain terminology is quite important and need to be explicitly clarified. And the formal verification reveals hidden assumption, like the aircraft weight. And LLM have some potential because of the high logical equivalence. We think the impact is LLM now is can bridge requirement verification gap for domain expert, but maybe in future we could do better. We also have like some future direction and conclusion we want to share with you. My future research roadmap will be introduce also some interactive refinement because sometimes we found because it's from the document some misunderstanding or we translate to the property is too strong or too weak cause the false count example and we need to do the specification improvement. The scalability problem, we're currently working on smaller program and also for like metrics and neural network is still not verifiable. We think program slicing like based on function could be a solution. And maybe we can introduce some looping variant to help the verification. Requirement quality feedback. Currently, we only based on the provided requirement document, but it's not complete enough. And we want to say, okay, could we improve it and completely verify the program or software, right? We have some small thoughts for requirement engineering community. We think a formal verification now is very easy and accessible for us. And we still think requirement engineering is very important because it's critical for automation. And the requirement maintenance gains even more importance from the verification workflow. I have some vision. I think requirement engineering would drive practical requirement verification adoption in the future. That's all. Thank you. Here is my email if you have any question about the paper. And here is my corresponding supervisor for this paper. And if you want any cooperation, please contact him. Thank you. Thank you so much. Bye.